lecture on business intelligence today, 27th of March 2025. We will continue our endeavor in network topology in the first part of the lecture. In the second part, we start a new topic. So, network topology. Okay, so we have seen that we can describe a network with in math with a graph, okay, which is a set of nodes and edges. And now we want to know what happens when a new node comes to the party. Okay, so this is a new node. Let's say new node. And we ask, what is the probability that this new node connects to an existing node that already has k neighbors. Okay, so this is the question that we are going to be asking, and depending on this probability we get different configurations. Okay. So this is just the question that we ask. So we have two types of nodes in this lecture. The first one is the random network. And the second one is the real network. Depending on this probability. Okay. So let's describe both of them and see what happens there for dynamics and so on. So the random network. So the probability that a node So you need to be on time when we do our lecture. Please be either online or in presence. Please be punctual, okay? This is 2 minutes before we start. At some point I will stop admitting people that are late. With K neighbors, attaches to a node, to a new node, in a random network is given by a Poisson distribution. With frequency parameter lambda. Okay, so the probability for a random network that x equals k, probability that our new node connects to another one with k elements is given by lambda hoch k times e hoch minus lambda divided by k factorial, where k factorial is k times k minus 1, k minus 2, 3 times 2 times 1. Okay, so this is the equation that describes the behavior of the probability of a node being added into a random network connecting to another node with k neighbors. Okay, Poisson distribution should be known from the statistic lecture in the second semester. Yeah, so the real networks behaves differently. So the probability that a node is connected, that's a node with k neighbors, attaches to a new node in a real network is given by a power law distribution with power exponent gamma. So the probability for the real network that a new node attaches to other existing node with k neighbors is given by k to the potence of gamma, of minus gamma, and gamma is between 2 and 3. You can, I already recommended a book you can look why gamma is between 2 and 3 in the book of Barabasi. Network science. Okay. So these are the two equations. Any questions? So far? So equation number 1, equation number 2. Do you have any questions? Please. Okay, so then let's represent this graphically, okay, and see the implications. Graphical representation. If this is the logarithms of k, the number of nodes, and this is the logarithms of the probability, either real or probability sub k. For the example of gamma equal 2.1, we have following behavior. This is t 10 to the potence of 1, 10 to the potence of 2, 10 to the potence of 3. This is 10 to the potence of 0. This is 10 to the potence of minus 3. So the first equation, the random network, behaves like this. Okay, so this is the equation number 1, random network. Okay, means that where nodes have little neighbors, the probability of attaching to the node is like this. Where nodes have medium number of networks, then the probability is around the peak is around the mean value of the number of nodes, which is around here. This value is the mean value of the number of nodes. The average, you don't want to use the word mean, the average. Okay, and then the number drops dramatically after being higher than the average number of nodes. Good. This is the behavior of the random network. The behavior of the real network is like this. Equation number 2, real network. As I said, this is for gamma 2.1. And this is remarkable, okay? Because this behavior describes these two curves cross in these points. Left to the first point, the real network is bigger. This is the blue line. In the middle of the 2 points, the random network is bigger. And on the right of the second point, the real network is again bigger. Okay. So we have the red line describing always the maximum of this. And this helps us describe the graphic in 3 areas. Okay. This is area number 1, left to the first point. Area number 2 in the middle. Area number 3 on the right. Okay. So let's comment on these 3 areas. In this area number 1, we can paint it with some color. This area number 1, the random network is way smaller than the real network. You see here, the random network is smaller than the real network. This implies, so for small k, the power law distribution of the real network is above the Poisson of the random network. Indicating that the real world has more nodes with few neighbors. Okay. This is the first area. The second area. In the second area, as you could see in the graphic, the random is higher than the real. Okay. Here, random is bigger than the real. So 4 nodes around the average number of neighbors. Okay. The random network has excess of nodes. And for the third area, and this is the characteristic that is going to be crucial, as we saw, the random network almost disappears and the real network is way bigger. So for large K, the real network presents nodes with high value of K. These nodes are called hubs. So these hubs, which are represented in this area, let's say here, these hubs presented here, are the characteristic of real networks. You have probably heard about influencers, maybe, in social media. Okay, influencers are nodes that have a lot of neighbors. Influencers are hubs. Okay, maybe you have heard about the airport in Heathrow, or the airport in Los Angeles, or the airport in Atlanta, or the airport in Frankfurt am Main. Those airports are hubs, or the airport in Abu Dhabi or in Shanghai. Those airports are hubs, are nodes that are very highly connected in the network of flight transportation. Okay, so these hubs are nodes that have a lot of neighbors and are crucial for network performance, because if one hub disappears or stops working, it's not the same as if one external node with fewer connections disappears. So if the Frankfurt airport stops functioning, it's worse than if the airport in Memmingen disappears and stops functioning for the performance of the network. Okay, this is basically the idea. Okay, so when you work on network analysis, it's important to know where your hubs are, and that's why we do this analysis on the this what we're representing is nothing but a degree distribution. We saw what that means the other day in the lecture. Okay. Good. Any questions, please? So last semester, this content was a question in the exam, okay? Please go ahead. Yeah, good question. So example for a random network. Imagine you are an Amazon warehouse, okay? And you are getting products back from customers, okay? So this is like a city, okay? Or let's say this is Baden-Württemberg. And you're getting from customers that are not happy with the products, you're getting product back, okay? And you're getting, let's say, a frequency lambda of 10 returns per hour. Okay? All right, please stay with me. Leave your microphone on and let's get a dialogue, okay? So you're getting 10 returns an hour. Is that okay? So I ask you, these returns are random, okay? Because they're coming from the people in Baden. It could be you, your friend, and some other people getting their product back because they're not happy with the product or the color or the size or whatever, okay? So we ask, what is the probability of getting exactly 3 products back in the next hour. Okay? So we say the probability of getting exactly 3 nodes, three returns is, remember, this is k, okay? And this is lambda, e hoch minus lambda, 10. Lambda, 10 to the potence of 3 divided by 3 factorial. So this is e hoch minus 10 times 10 times 10 to the potence of 3 divided by 3 times 2 times 1. Okay? If we do that with our calculator, 10 in negative, let's say this is our exponential, times 3 in negative equals, on this divided by 3 and divided by 2. So this is 3, 6, 10. This is 7.5. 10 hoch minus 10. Okay? So this is the probability that you exactly get 3 returns in the next hour. Okay? Why? Yeah, klar. Yeah. Yeah. E is 2.7 something. So why is this the case? We have a random, and this is the important part, this is what answers your question, random number, a random network, sorry, of customers that are returning their products independently from each other. Okay, yeah, no problem. Give it to me. I probably made a mistake. Tell me. Okay, very good. Thank you. It's difficult to make it with iPad, laptop, and moderation and everything. Thank you very much. We trust you better than my result. Okay, so I didn't read your name properly. Can you come back? So, yeah, no problem. So is your question answered? So we have here a network of people that are independently from each other returning their products, okay? And we want to know the behavior of this network returning. So is your question answered? Good. Any more questions? So the more you ask, the more you will learn, okay? Because we go deeper and deeper. It's no problem if you ask a lot. It's actually a better lecture if you ask, okay? So yeah, so that's the behavior of random and real networks. There's a lot more, but this is the basic. If you want to learn more about this, feel free to go to that book. Okay, Network Science by Barabasi. So questions, please. Need some feedback if everything is cool. Yeah, Leon looks good. Only Leon. Also, all right, good. Thank you. Then we continue with a different topic, which is very important because it starts getting into the intelligence, let's say, of the business. We start with deep learning. Deep learning. Okay. And we do deep learning here in this lecture, not by programming, we do it by hand. So basically what you learn here is the basics of deep learning by doing the calculations yourselves. Okay? And this is very important because then you understand really what is going on. Okay? So we start with the very first, the easiest, it's not even deep yet, the easiest case, which is a single neuron. So only one element of the network that will later do the deep learning. So imagine if in the brain you have billions of neurons, we only have one now. And this is called perceptron. And this is actually the reason why we are looking at networks before, because networks, learning in intelligence happens in networks. That's why we saw the networks earlier. So, but now we focus on a single neuron, okay? Single neuron, which we call perceptron. The neuron has a vector of inputs. I try to do this as slowly as possible. So these inputs can be numbers or can be features. Is what we are inputting into the network, what your eyes is seeing. These inputs are multiplied by some weights. Okay, so this is the input. These are the weights that we are going to learn. These weights are added up into a single value. Then we apply something called this is the actual neuron, okay? Then we apply some so-called activation function. And then we get one output. Remember, we had an input, we get an output. So we input some image and we get the recognition that is a car or a tree. But we have here one measurement of the output and we send it back for adjustment. This is the measurement, is called Y with hot. And our error is going to be the measurement minus the expected output, or the expected output minus the error, minus the measurement. Doesn't matter. And this is how we learn in the perceptron, okay? This is the basic principle of deep learning. We have a vector multiplied by some weights that are added up in the perceptron neuron, and then we have an activation function, and then we send all this through our error back, and get a learning loop. Okay, so this happens, of course, step by step. We are going to go through the steps. The first step is this part. Step 1, what we call the feed forward. Second step is the applying the activation function. Step 2. Step 3. Let me get another color. Step 3 is the applying of the error. And step 4 will be to do here the adding up, what we will call the gradient descent of a calculation. Okay? Sure. What? Yeah. You're right. We are multiplying. Yeah. Thank you. You're right. We are multiplying. So the step 1. We multiply all input values x sub e with their corresponding weights w sub I, and then calculate the weighted sum. Okay. Step 2, we apply an activation function to step 1. So what are these 2 steps meaning graphically? Now, in order to put it in a graphic form, I need to do it in 2 dimensions because it's only, so n being 2, because otherwise I cannot represent it graphically, but this happens for n dimensions. Okay. What is happening? We are describing, as I said, in 2 dimensions, a line going through the origin, which is of the form x sub e, w sub e in sum. Okay, this is what the perceptron is representing, is a linear representation of the function. Okay? And we then apply the second step. we apply a function to this line to adapt it to our data. Okay, so this it's going to be like applying the function and adding a bias. Okay, and this is what we call y with a hat. This is our measure. Okay. Examples of activation functions used in deep learning. There are many. There are many. I give you two. One is the step function. This is the first one that was used. So it's the easiest computation-wise. We have the step function goes like this. It's 0 for all values below 0 and then 1 for the rest. Okay, so this is the step function. Looks like a step. 0 if x is smaller than 0 and 1 if x is bigger than 0. Okay, so this eliminates all negative values. And the second one, which is the one we will be using, is a little bit more challenging, is the rectified linear unit. ReLU, which is a little bit more challenging. As I said, it's 0 for values negative and a line for values positive. So the rectified linear unit is like this: 0 for x smaller than 0 and x for x bigger or equal 0. Okay, so I'm explaining right now, I'm explaining the theory. Okay, later on we will do plenty exercises and you will get a grasp, but you need to come back to this theory to understand. So we won't need to calculate the weight values which make our error minimal. So we take the squared of the difference Remember, when we have a difference, we are having a distance in a Euclidean domain. Between expected and measurement. So expected is y, expected value. We want to be a car or a tree. Measurement equals the function of xy, wy plus the bias. And we want to minimize y minus y square, y minus y with hat square. Okay, this is called quadratic error. So we use the quadratic error in order to avoid canceling of positive and negative values. Okay, so our final cost function to be minimized is going to be 1 divided by 2. We do it because we have two variables, y and y with a hat. It doesn't change anything in our calculation. Y minus y with a hat, and this equals 1 divided by 2, y minus the function, the activation function applied to the linear approximation. Okay, so this is basically what our perceptron is doing. It's finding the minima, the weights, so that this function is a minimum. The perceptron adjusts the weights W sub e so that this cost function or quadratic error is minimized. Okay. Any questions? This is just the theory, okay? So we will take our time, but this is what we do. This feedback loop that we described here is nothing more than adjusting the weights that we are describing here. So we start with some random weights and then we adjust them in learning process. And this is called learning, okay? Adjusting these weights is what we called learning. Okay, so questions? So the derivatives of this cost function z of the weights vector are called gradients. So if we have the first derivative of the cost function to a given weight, we do the derivative of this function is very straightforward. It's y minus y1 y2 minus yn xn multiplied by minus x sub e. Okay. And in order to get the minima, step 4, in order to get the minimum of the cost function in a parenthesis we learn, okay, we want to find the values that make these gradients 0. Okay, just when we find a minima of a function, we want the first derivative to be 0. We do so by adjusting the weights by a small amount and this amount is called learning rate. Okay. So basically we have, again, let me paint it again. We have a vector of an input multiplied by another vector of weights in which we apply a certain linear multiplication, adding a bias, then we apply a function, an activation function that takes us out of the linearity. Then we get a measurement. We put that back into our system using a cost function. So we saw already. It's a feedback loop. And what we get is two behaviors. One is the feed forward, what we call the feed forward. And the second behavior that we need in order to learn is what we call the back propagation. Okay? And this is the principle of deep learning. This is the principle of 95% of all artificial intelligence that you see today. Intelligence, okay? That you see today. This is the principle for ChatGPT. This is the principle for image recognition so that your phone can recognize your face. This is the principle for a bunch of shit that is going on in the market right now. Okay, this little learning loop. And remember, this is only one neuron, okay? So it's amazing what we do with our brains when we learn. And this is the reason why we still don't understand it yet, because it's super complex. Okay? So welcome to Artificial Intelligence 101. Willkommen in der Welt der künstlichen Intelligenz, in Anführungsstrichen Intelligenz, 101 für Anfänger. Ich denke, I think this is really cool to learn this way, to learn it this way, but I need you to take a piece of pen and a piece of paper and do the exercises that we will do after the pause in detail, okay? If you want to learn this, you need to study hard. No shortcut. Es gibt kein kurzer Weg, ihr müsst es wirklich lernen, ansonsten gibt es nichts. Gut, gibt es Fragen? Are any questions? So in my opinion, this is really cool stuff, but you need to, and this is also up to date. This is really state of the art. Es ist halt notwendig, dass ihr lernt. Es ist aber KI steht auch nicht in dem Programm. Ich denke, es ist aber notwendig, dass meine Leute, die Leute, die mich berühren, in den Vorlesungen das lernen. Deshalb unterrichte ich das in der Business Intelligence Vorlesung und nicht andere, vielleicht theoretischere Themen. Gut, so our topic, deep learning by hand. And we will now start with exercises, okay? So example 1 will be one single neuron with just a feed forward. Example 2 will be the output of 2 layers, not only just one neuron, but layers, 2 layers of neurons, and so on and so forth, okay? So we will just extend, go step by step, incrementing, increasing the complexity of the system, okay? So make sure you repeat these exercises with different numbers because this is going to be relevant for the exam. So example 1, is called single neuron perceptron forward pass. All right? So here we have an input vector of 3 numbers, 2, 1, and 3. Just some numbers. This will be like x1, x2, x3. Okay. We have a initial vector of weights of 1, -1, 1. This would be like weight 1, weight 2, weight 3. And we have an initial bias of -5. We can represent this like this. We can say -1, -1, 1, -5. Okay. This would be like weight 1, weight 2, weight 3, plus the bias. Okay. And we've got here our input vector 2, 1, 3. All right, which this is like x1, x2, x3. That cool? Just super easy representation of what we're doing, right? So now we want the output of the forward pass is this y with a hot. Okay, this is the feed forward pass. So what we want is to perform this calculation. Y with a hot is the activation function. We will use a ReLU. And then apply to the output of the neuron, the weights multiplied by but for some reason, people have problems understanding this notation. So I will do it graphically. First, I will do it graphically, then we do it with the math, okay? But this is the same. It's just different way to put the information. So if we multiply weight 1 times x1 plus weight 2 times x2 plus weight 3 times x3 and we add b. Okay, and then we apply to it some function. We have exactly the same as we had above. Y with a hot. You agree? Right? It's exactly the same. So let's do it, but let's do it with a picture. Because as I said, for some reason people have problems. So I will just write the F and then just follow me in the picture with colors, okay? Just like for babies. I multiply y1 with x1, which is this, okay? What is multiplying 1 times 2? That cool? plus, I take another color, minus 1 times 1, which is this, minus 1 times 1, plus W3 times X3, well, let's take another color, no problem, 1 times 3, 1 times 3, then I take another color yet and go ahead and add up, like plus minus 5. That cool? Could you follow this way? This is super important, okay? Oh, no shame in saying, hey, I don't understand. No shame at all. So I hear nothing, so I assume this is understandable. So I just copy the F again. We'll take care of the F later. Then I say 1 times 2 is 2. Minus 1 times 1 is minus 1. So if we add it up, then I get a 1. Plus 3 is 4. Minus 5 is minus 1. So the result of that is minus 1. I mean, if you have problems doing that, just take your calculator and do it, but I just do it in my mind. So the result of all this is minus 1. As I said, it's just multiplying 1 times 2 is going to give 2. Plus minus 1 times 1 is going to give minus 1. So if we add it up, it's just plus 1. Plus 1 times 3 is 3. So plus 1 plus 3 is 4. Plus minus 5 is going to be minus 1. So I take again another color. We are here happy with colors. Here, and then I said, so this should be like, so we say that our F is our rectifier linear unit, which goes like, gives a 0 if the x is smaller than 0, gives an x if x is bigger or equal to 0. So because our minus 1 is smaller than 0, our rectifier linear unit is going to be delivering a 0 because minus 1 smaller than 0. Okay, is that step cool? So this is this result this is this part. Then we apply our f ReLU function. And then we get as a result this part 0, which is the answer we're looking for. So I really tried to explain this thing a step-by-step manner. Any questions? Do not hesitate to ask. So bitte fragen, falls irgendein Schritt nicht verstanden wurde. No, you don't need them. Just to make it more clear. You can avoid the 2 brackets actually, yeah. You don't need them. I just thought that was easier to understand. Okay, so no questions. Good. Then let's expand. If you understood this, then it's good. But it's not by far the end of the story. Okay, so let me plug my computer before I run out of gas. Not the end of the story. Okay, so we're still gonna do a second example today. But still, I mean, you are learning the basics, the very basics of artificial intelligence. Okay, so you should be proud and challenged, feel a little bit of excitement, okay, because this is really cool stuff. So example number 2. Calculate the output of the forward pass of 2 layers with 2 layers of perceptrons with 3 and 4 neurons. So things get more tricky, of course. Things are getting trickier and more complex with each example. So now we have 2 layers of fully connected perceptrons. The first layer has 3 neurons. So we have 3 inputs, x1, x2, x3, going into each neuron. Okay, so this is our vector of inputs. And the second layer has 4 neurons. So 1, 2, 3, and 4. Okay. And we get here a vector of outputs. This is what we are asking. And it's a fully connected thing. So all neurons are connected to all others. This takes now a little bit to represent, but it's just necessary for clarity purposes. So all neurons are connected to all others. Okay. And the union of one neuron to each other are the weights. So, for instance, we connect neuron 1 with 1. This is the weight 1, 1. If we connect neuron 3 with 1, this is connection, 3 with 4. This is connection 3, 4, and so on. Okay? So this is just the way it works. Let's represent this in a way that we can solve the problem. So you still with me? Good. Then let's put this problem in numbers. This is actually what you will need to be doing when we, if I ask this, and I will ask about this in the exam for sure. So make sure you practice plenty of times. So our input vector is going to be 2, 1, and 3. Okay, this is our x1, x2, x3 numbers. Then we have a matrix giving us the weights, and it takes a little bit of time to do this, but I like it to make it pretty clear and neat. Then it will be easier for you to learn and to follow up. So in the exam you don't need to do it so clean. In the exam it needs to be correct. Okay, so make sure you practice. Practice will give you speed, and speed will give you points. And points will give you a good grade. So we have the weight matrix. Now it's a 3 by 4 matrix because we have 3 by 4 neurons. 3 by 4 connections. So I'll take just some numbers. So this is our weight matrix. Here. This is W. And then we have some bias, -5, 0, 1, -2. This will be our bias representation, so our vector of bias B. This is X, as I said. Okay, so this is the input of the problem. Now we want to solve the feed forward. Pass. So what do we do? When we do this? And this is after applying the ReLU function. And this will be y. Okay? So we want to calculate f of the sum of x sub I times w sub I plus b okay, this is the activation function of 2, 1, 3, the x vector multiplied by 1, 1, 0, 1 minus 1, 1, 1, 0, 1, 0, 1, 1, and then add it up to minus 5, 0, 1, minus 2. Okay. As I said, for some reason people have problems doing these matrix multiplications, so I will do it graphically, at least for the first example. I will do it graphically. So here we multiply 2 times 1 minus 1 times 1, 1 times 3, and add it up to minus 5. Okay, so again, in this notation below, what we do is we multiply this, this times 1, 1 times minus 1, 3 times 1, and add it up to minus 5. Okay, so 2 times 1 plus 1 time minus 1 plus 3 times 1 plus minus 5. If you do this, this will give you minus 1. So this is f of the first position is minus 1. So you need to write here, I painted in different colors, so minus 1. Okay, so this is minus 1. So you cool? All right, so we just perform the same thing. So now 1 time 2, sorry, or 2 times 1, I follow with the same. 2 times 1 plus 1 times 1 plus 3 times 0 plus 0. This gives you 3. So 2 times 0 plus 1 times 1 plus 3 times 1 plus 1 gives you 5. And then 2 times 1 plus 1 times 0 plus 3 times 1 plus minus 2 gives you 3. So this is 3 and this is 3. Because f is ReLU, negatives are being zeroed, the positives are left the same, so this is 0, 0, 3, 5, 3, 0, 3, 5, 3. All right? So, we cool? This is a fully connected perceptron layer. And that's why we get a matrix here, okay? The connections are represented by the matrix. But right now, what you're doing is you're learning deep learning, okay? And this is really hot shit. So, closest.